Hi there. In today's video, we'll be covering the second session of probability distributions. In this video, we'll be covering the probability distributions of continuous random variables. So in the last video, we talked about random variables. We talked about discrete random variables and different types of distributions which are associated with discrete random variables. So today, we'll be covering continuous random variables and some of the distributions which are generally associated with it. Okay. We also try to understand what is the probability density function for all of these. We'd also learn about the probability density function and the parameters with respect to some of the distributions of continuous random variables. So what is a random variable? That is something which I've already studied before, just to give you a quick recap. And this is just to show you some of the examples of continuous random variables. Okay, so vibration measurements, temperature measurements, calibration, length, volume, area, sales, age, time, weight, all these parameters or all these attributes typically follow on a continuous distribution. Okay? And the possible outcomes is, 0 to infinity. So it's like, our side can be minus infinity to plus infinity. So the range is pretty high with a lot of unique values. The unique values will be, the number of unique values will be as much as the number of variables, number of values in the data set, right? Which means that there are hardly any repeating values, right? So that is where continuous random variables will come to the picture. Now, if you look at the probability distribution of continuous random variables, it is noted by f of x. So in discrete random variables, we are using, p of x. In continuous random variables, typically we denote it by f of x. You can also use p of x, not a problem. And the second most important point is to understand that a probability for x, which is a continuous random variable, for it to take any single value, its probability will be. So the probability for x to take any single value, a, that is a less than equal to x less than equal to a, which means that one single value, x is equal to a, and the probability is 0. Since the random variable is not discrete, since it is continuous, we cannot find out the probability of an event, right, equal to some particular value. In previous case, when we did Poisson distribution and binomial distribution, we took out, right? We extracted probability of x equal to 0, x equal to 1, at x equal to 3, because they were discrete data points. But here, the x is continuous. So we cannot find out the probability at a particular value of x. It's not possible. Why? Because the probability function is a curve because it's continuous, right? And for that reason, we won't be able to find a probability of an x at a particular data point. So we create a histogram. So histogram is an approximation to a PDF where we create intervals and then we find out the frequencies or probabilities of the respective intervals. I think showed you this example in the, when we tried studying measures of central tendency, right? In the second or third video, correct? And this is nothing but my histogram, right? And this histogram area under this f of x will always be equal to, total area under this f of x will always be equal to 1, okay? And we can only find out probabilities between certain intervals. So what do I mean by that? It simply means that the probability density function PDF, it will always be greater than equal to 0, of course, and the area on the total curve, which is minus infinity to plus infinity, which is given here, will always be equal to 1. Total probability, right? Simply means total probability. So if I have this, so the entire area here, the probability will be equal to 1. That is what it basically means. So here also it is indicated by this. For a continuous random variable x, this should be at any value x or x at any value, say 2, 3, 4, like that. Discrete numbers we cannot take, and we cannot capture the probabilities of discrete numbers. The probability will always be 0. Okay, and the probability of x lying between two data points, right? That is what we can find out. So we can always find probabilities in intervals, in between intervals, right? And whenever we have in between intervals, so suppose this curve which we have here, and when you find out, say, let's say I want to find out the probability of X lying between 10 and 20, okay, 10 and 20, then area under this curve will give me the probability between A and B, which is 10 and 20. Okay, so which means that I here cannot do probability of X equal to 10 plus probability of X equal to 20. No, this plus sign is something which we use for discrete random variables. For continuous random variables, I have to integrate it from 10 to 20 f of X dx or p of X dx, whatever you call it. So this is called as cumulative probability because we're summing it up. It's accumulation. Correct? Because probability X at X equal to 10 for a continuous random variable is always 0. At any point of value, at one discrete data point, you cannot find out because it's a curve. Okay, we can always find out between intervals. And to find out between intervals, we can simply have to integrate it. Because once we integrate it, it will give me area under the curve. And area under the curve is nothing but my probability. Very simple, right? So here we can see that the probability of that particular X between those two intervals actually do not matter whether the interval value is included or not. So whether it's X1 less than equal to X, or whether it's X less than equal to X2, or simply less than X2, it doesn't matter. When I want to calculate probability between two intervals, it's just between A and B. So all we have to do is integrate from A to B. Earlier it was mentioned as B to A, I guess. So I've rectified it. It should be from A to B in this case. And you can see here, this is the probability density function. It's a curve, right? So if I have to calculate the probability between any two intervals, say A and B, I have to calculate the area under the curve between these two intervals to get the probability. So probability at X equal to A will be 0 because at one particular point, we cannot find out. It's always have to be found out between two intervals or less than that interval or greater than that interval. It has to be interval. There has to be intervals. That's what I'm trying to say. If you move to cumulative probability, right? It's almost the same thing, but just that cumulative probability by definition means that we can find out the cumulative probability of continuous distribution function as well. And the difference between CDF and PDF is that the limit changes from minus infinity to X. In probability density function, it was from between A to intervals, A to B, C to D, whatever it is. But in cumulative, it's always from minus infinity to a value of X. So here, let's say X is some value. So the cumulative distribution will be this point, minus infinity to X. Not from 0 to X, please understand, because X can be negative and positive as well. So it's minus infinity to X. If your distribution is such that it does not carry any negative value, then it will become from 0 to X. Okay, well, in this case, we do not seem to have negative value. So in this case, we from 0 to X. The probabilities here are very less, the area is very less. Doesn't matter, but it has to be from extreme left end to the point at which you want to find out the probability. So this is also interval only, minus infinity to X, 0 to X, same thing. Just that for cumulative, you need this will be from minus infinity if your random variable can take negative values, or it will be from 0 to X if it cannot take negative values, if it's all positive values. Clear? Okay. So the first distribution, continuous distribution, which you are going to cover today is normal distribution. So let's look at the parameters of normal distribution. So normal distribution consists of two parameters, and they are namely mu and sigma, mean and standard deviation. Okay, the variance is given by sigma squared, standard deviation squared, and notation is given by n of mu comma sigma squared. So this is the mean, and this is my standard deviation. Something which you have already covered in understanding sample and population, right? However, the most important point is that f of x, the probability density function, is given by this formula. But who cares about formula, right? We don't need to remember any formula, but this just to show you the complexity inside normal distribution. Distribution seems so, simple, but actually, if you look at it, it's the derivation part of it, especially the equation, is not that simple. Now, if you look at this, right, this will give a fairly good idea of how the sigma and the standard deviation, how the mu and the standard deviation, mean and the standard deviation affect the normal distribution shape, right? So if you look at this is sigma square equal to 1, which means that variance is 1. Here, variance is 4. So you can see here, as the variance increases, my curve becomes more flat because the range will increase, right? Higher range will, higher range with more extreme data points might lead to a higher variance. Same mu, same mean, but the shape has changed due to the standard deviation or the variance change. More the variance, flatter will be the curve. However, mu is equal to 15. If you look at it, standard deviation is same as 1, like this. Shape is same, but the location has changed because mu has now changed. Mu is the average value of x. Okay, and x obviously is in ascending order magnitude from left to right. Correct. So mu is sometimes also called as a location parameter because it tends to give you an idea of the location of that graph, whereas variance or standard deviation can also be referred to as shape parameter because it tells you about the shape of the graph, how flat it is, how sharp it is. So these are also called as location and shape parameters. Now, if you look at the cumulative distribution function, it will be the integration from minus infinity to x of f of x dx. So right, this is this particular function. And if you look at it, this integration is not going to be easy, guys. Right? This integration is definitely not going to be easy because you are integrating with respect to e to the power of x squared, like square of the exponential function. So with this, right? So scientists have found out other ways to convert this normal distribution to a much more easier format, and that is called a standard normal distribution. Okay, but before we go to that, I just want to hint out a little empirical rule of normal distribution. So on the properties of a normal distribution, which says that within mu plus minus sigma, plus minus 1 sigma, mu minus sigma to mu plus sigma, 68% of those data points, of the entire data points, will lie within this region. Okay, 95% of the entire data will lie between mu plus minus 2 sigma. 99.73 actually percent of the entire data set will lie within mu plus minus 3 sigma. So mu plus minus 3 sigma, if you look at it, if you find out difference, mu plus 3 sigma minus mu minus 3 sigma, if you want to see the range, this actually becomes 6 sigma, right? 6 sigma range. So that's why we have 6 sigma Bell certification, all those things. It's derived from this. But these percentages are nothing but empirical numbers, which means that people have gone through, researchers have developed these numbers or extracted these numbers or calculated these percentages based on empirical results or experimental results. Correct? There is one more famous researcher who was called as Chebyshev group, who is a different approach towards calculating these percentages of data point between different in levels of sigma, plus minus sigma. Okay, but we'll cover central limit theorems and all these things in greater detail in the upcoming videos. Okay, now let's move forward to standard normal distribution. So we understood that this distribution function of normal distribution is not going to be easy to interpret, right? Every time think about it while calculating simple probabilities between any two intervals, it will be very difficult for us to integrate over the f of x dx. So researchers have come up with a solution for this, and they have developed the standard normal distribution, right, to make our tasks much more easier. Now, if you look at this, standard normal distribution is nothing but a normal random variable, but with mu is equal to 0 and standard deviation is equal to 1, or variance is equal to 1. Okay. Right. So its parameters changes to n of mu comma sigma. So mu is 0 and sigma is 1. It is often denoted with the letter capital Z. The CDF is defined by the phi of Z, of course, just like we did before. And these cumulative values are now calculated, have already been calculated for a range of possible numbers in a table which is called as the standard normal table or a Z table. And a Z table looks like this. And all these entries which you see here, these entries refer to the probability or area under the curve from minus infinity to that value of X on this graph. Okay, so basically what I'm trying to say here, if I want to find the probability if I want to find the probability of Z such that it is less than, say, 0.26 on the left hand side, 0.26. So here we have to go to Z, 0.2, and 0.06, the second decimal place is here. So we travel like this, and 0.6, so this is my probability. 0.6026 is my probability of Z less than 0.26. And by the way, for standard normal distribution, your mean is 0, right? So Z will, so if this is 0, right, Z 0.26 will lie somewhere here, right? That's why its probability is higher than 50%, because the standard normal distribution is perfectly symmetrical, just like normal distribution. And at the point where the Z value is 0, your area will be 50%, and this side will be 50%. 50% for negative value, 50% for positive values. Since it has been standardized, the mean has become 0. It becomes very easy for us to understand. And both these sides are symmetrical. Okay, so you can see here at Z equal to 0 with less than equal to 0. For Z less than equal to 0, my area is always 50%. Okay, that is what it means. Minus infinity to plus infinity. Clear? Okay. All right, we'll take some more examples to understand the Z table more clearly. But again, guys, we don't need to remember any formulas which I've shown you, just for educative purpose, so that you can relate to what you've been learning in your institutions. All these probability calculation functions are all easily available in Python and any other language as well. In Excel also we can do that, right? We don't remember all these formulas, but we need to understand them. What was the story behind it, that these distributions have been changed to standard normal distribution. Okay, so let's have a look at how we calculate probabilities from the Z table. Although we do not require a Z table if we have Python. Okay, but just to understand it, let's check it out. Say I want to calculate the probability of Z less than, such that it is less than 1.26. So basically what I'm asking, this is the curve, and by the way, this value Z mean cannot be 1.26 because it will always be greater than 0, right? So let me rectify this. So let us now take some quick examples to understand how to read the Z table. Okay, let's say if I ask the question, what is the probability of Z such that it is greater than 1.26? Okay, so let's look into the graph. So this is the normal distribution graph. This is my Z is equal to 1.26. So this is the area which I want, probability of Z greater than 1.26. But if you go to the previous slide, the table which we had was actually given for probabilities which are less than that particular value. Right? So can we do something like this where we can calculate? So can you do something like this? So probability of Z greater than 1.26 is nothing but, so probability of Z greater than 1.26 is equal to 1 minus probability of Z less than 1.26, right? So probability of Z less than 1.26 is this area. So this area on the left-hand side, which is here, is P of Z less than 1.26. So you can simply subtract this region from total probability, which is always equal to 1, to get probability of Z greater than 1.26. So all you have to do is calculate probability of Z less than 1.26 from the table. So let's do that. So if you notice here, probability of Z less than 1.26. So 1.26. 1.2 is on the vertical axis, and 0.06 second decimal place will always be on the the horizontal line. And if you want to narrow down, you have to plot this. And if you want to narrow down, you have to go. And if you want to narrow down, you have to do this. And finally, I get the value, which is 0.8962. So 1.2, right? So 1.2 is this value. 0.06 is this. So 1.26. And when you go towards this line and we go vertically down to get the intersecting point, which is 0.8962. And this value is probability of Z less than 1.26, guys. Please remember that. Okay. So once we have that value, so what we can do next? So this was the graph which we had. So we can basically simply equate it to 1 minus 0.8962, which is our value from the table. And then we can minus it from 1 to get 10%, right? So this value which you see here is from the table, and we subtract it from 1 to get 10%, which is this region. So my answer is probability of Z greater than 1.26 is equal to 0.1038. So that is how we calculate probabilities of standard normal variables or values from the Z table. So what we have here, finally, we calculate the P of Z greater than 1.26 as equal to 1 minus P of Z less than 1.26. So P of Z less than 1.26 we have already calculated, which is around 0.8962. We subtract it from 1 to get 0.1038, which is roughly around equal to 10.38%. So the probability of Z greater than 1.26 is equal to 10.38%. So this is how we calculate probabilities from the Z table. Now let us take some more examples to make our concepts much more clearer. So if you look at this table, right? So let's go one by one. So this is what we did here, right? So let me pick up the first question, probability of Z greater than 1.26. So in the table, we have all positive values of Z, and that too only for Z less than values, right? So we have to calculate this region first from the table and subtract it from 1 to get 1.26. Next, probability of Z less than minus 0.86. Again, negative values are not given. Less than values are given, but negative values are not given. So probability of Z less than minus 0.86 will be same as calculating probability of Z, which is greater than 0.86, because both these two halves are symmetrical. So again, probability of Z greater than 0.86, greater than values are not present inside the table. So again, what we'll do, 1 minus probability of Z less than 0.86. So ultimately it is 19%. So this area is actually 19%. So probability of Z greater than minus 1.37 is again greater than values is not given, negative values are not given. So probability of Z greater than minus 1.37 is same as calculating probability of Z less than 1.37. Right? So this area and this area is the same, right? And this area we can easily find out from the table because probability of Z less than the positive value, which is 1.37. So how does this conversion takes place? How did we convert the normal distribution to Z distribution or standard normal distribution, right? With mean 0 and 1. So let's see how we convert it. So let X be a normal random variable with mean mu and variance sigma square. We all know that. P of X less than X is equal to, this is my general expression. Okay. Now, if I want to convert X to a random variable Z, I have to do X minus mu by sigma. So Z is equal to actually X minus mu by sigma. This is how we convert normal to standard normal distribution. So once we have this, here now Z is a standard normal variable and Z is equal to X minus mu by sigma, and is obtained by the standardization of X. This in fact is a method to standardize your data. When you go to exploratory data analysis and pre-processing techniques, when we have continuous values in very different scales, we scale it using this. right? We have a function which is called a standard scalar, right? In sklearn Python. Okay, so probability is then obtained with respect to the z value, for which we already have a z table. Again, we don't need to refer to z tables in the corporate because we do it simply using Python. Okay. So now if you look at this particular figure, right, here we have the here we have the normal distribution with mu and sigma as variance. And when you convert to a standard normal, my sigma becomes equal to 1 and my mu always will become equal to 0. Either side, both of them will be symmetrical about the mean. Okay, the graph will be symmetrical about the mean. So let us take an example to understand this conversion of normal distribution to a standard normal distribution. Okay, suppose the current measurements in a strip of wire are assumed to follow a normal distribution with a mean of 10 milliampere and variance of 4 milliampere square. What is the probability that the measurement will exceed 30 milliampere? So basically they're asking about the probability that the current will be more than 30 milliamperes. So what is given to us? Let's say X, not the current measurement. My mu is equal to 10 and my sigma is 2 because my variance is 4. Root over 4 will give me 2. So what is being asked? Probability of X such that it is greater than 30. That is what is being asked. So this, I can equate it to this because by using date transformations on both sides of the inequality. So X will be converted to X minus mu by sigma. Similarly, on the right hand side, 13 will be converted to 13 minus 10 divided by 2. Correct. So next what we'll have P of Z greater than 1.5. So P of X greater than 13 has been converted to P of Z greater than 1.5. But this is not something which will be given in the table because in table we'll record P of Z less than 1.5. So I'll convert it to 1 minus P of Z less than 1.5. So you can see here the conversion how it happens, right? Okay. So once this is done, so this is something which I can easily extract from the table, and that value is 0.9332. So once I get it, I'll subtract from 1 to get 0.0668, which is roughly around 6.68%. So the probability of X getting 13 is equal to 6.68%. There's a 6.6% chance that I may have a current value which will exceed 30 milliamperes. Right. So this is the area. So there's a note here. So the probabilities for any normal random variable can be computed with a simple transformation to a standard normal random variable. So any normal distribution can be converted to a standard normal distribution. You can find out the probability with respect to any normal random variable by simply converting to a standard distribution. So the next distribution which I'm going to cover is called as log normal distribution. So what is log normal distribution? A log normal, or log normal you can call it. A log normal distribution is a continuous probability distribution of a random variable whose logarithm is normally distributed. So what does it mean? So basically what it means is if a random variable X is log normally distributed, then the log of X is actually has a normal distribution. Right? So if a random variable is log normally distributed, the log of that particular random variable is a normal distribution. And some of the examples are like this, right? It almost looks like a normal distribution, but generally it tends to have some kind of skewness. Okay. One more thing which is very important to remember, guys. Is that the parameters of the distribution will change now. It will no longer be the mu and sigma which we had before. The mean will be the mean of our log normal distribution will be a function of the mu and sigma of the normal distribution. Let's have a look at the parameters. So these are my notation. So notation is called as log n. Okay, it's called as natural log of n of mu comma sigma square variance. Parameter sigma square greater than 0, distribution X greater than 0, of course. Now log X, right? Value is always greater than 0. Sorry. So for log X to happen, right? To find out the log of a random variable, x has to be greater than 0. Log of negative value is undefined. Log of 0 is undefined. So it has to be greater than 0. The PDF expression now is somewhat more complex than the one which we had before, right? Even the CDF is complex. The mean value which you see here, right, is a function of the mu and sigma. So this is the mean of the log normal distribution. This is the variance of the log normal distribution. Okay. Similarly, we have other kinds of distributions like Weibull, Gumbel, all of them. And all of their means and variance are functions of mu and sigma, which is the mean and mu and standard deviation, mean and standard deviation of normal distribution. So here the mean mu and sigma which you see are the parameters of the normal distribution. But if I ask you what's the mean and variance of the log normal distribution, they are functions of the parameters of the normal distributions. So all other distributions seem to have originated from the normal distribution. That's why their own mean and variance are functions of the parameters of the normal distribution. But we don't need to really bother about these formulas and syntaxes because all of them can be easily calculated with the help of Python functions. But to understand these concepts and know about the theorems is very, very important, guys. Okay, so that's all for today. In today's video, we had explored continuous random variables and the various distributions associated with it, normal distributions, log normal distributions. We also saw standard normal distribution, how we convert normal to standard normal, and how it makes it easier for us to calculate probabilities from the Z table, although the Z table is not required because we'll ultimately use Python functions to evaluate it. But still, it's good to know because in institutions, you might as well be relying on Z tables and T tables, right? Okay. So it's very important that you know these concepts. We also did some examples of standard normal distributions, and we got to know that any normal random variable can be converted to a standard normal random variable. And once we do the conversion, it becomes very easier for us to do the calculations because we can directly calculate the Z value from the Z table. The probabilities from the, you can easily calculate the probabilities from the Z table. So guys, I hope you liked today's session. And from next video onwards, we will be starting off with hypothesis testing, which forms the inferential statistics. So the next few videos will be very, very important, guys. Stay tuned, keep practicing. See you in the next session.